Okay, we left off with the heating curve practice here. Now we're going to try a few more complex problems. These ones get a little challenging, maybe annoying. So this first question, how much energy would be required to turn 25 grams, so there's our mass, of ice at negative 25 degrees Celsius? Remember that ice can, get down to negative 273 degrees Celsius. Ice can be much colder than zero. And then into steam at 150. So again, I like to get my sample heating curve. So ice at negative 25 is going to be down here. Remember, water is the only heating curve I think I really want you to remember the specific values for, just the 0 melting point and 100 boiling point. So first, let's decide where we're starting, negative 25 degrees Celsius. Next, we're going to steam at 150. So we're not just boiling that water. We're then going to increase the temperature up to 150 here, somewhere around there. So now to get from this point to this point, we have to do 5 things. First, we have to increase the temperature of the ice from negative 25 to 0. Then we have to melt all that ice. Then at this point, we're going to have water at 0, and we need to bring that water temperature all the way up to 100. Next, once the water has reached 100, we need to boil that water. Turn it all into steam. Then once we have steam at 100, we can now increase the temperature of that steam up to 150. So it looks like we have 1, 2, 3, 4, 5 sections of a heating curve in this one little question. This is from these 3 little numbers here. So although this might be long and obnoxious, if we can do this problem, we should be able to do any heating curve problem like this. So we're going to do 5 things. First, let's do the MC delta T for the ice. So the mass will remain the same for this whole problem. So we have 25 grams. Now again, the specific heat of ice might not be the same as liquid. And we look on our specific heat table here, and we notice that it wasn't. It's 2.11 joules to raise 1 gram of ice 1 degree Celsius. So 2.11 joules per gram degree Celsius. And now what's my delta T? Well, the melting point of ice is 0, or water is 0. So we need to go from negative 25 to 0. That's a delta T of 25 degrees Celsius. We multiply this out and we get 1320 joules. Okay, so now we've increased that ice from negative 25 to 0. Now we need to melt that ice. That looks like a mass times heat of fusion type problem. So we have 25 grams. The heat of fusion is 334 joules per gram. And that means we're going to have to apply 8,350 joules to melt all that ice. Okay, now the ice is at 0. Now we got to do MC delta T again. And we're going to raise that 25 grams of water at 0 to water at 100. So we have 4.18 joules per gram degree Celsius. Again, that's my specific heat of liquid water. Now we're going from 0 all the way up to 100. That looks like my delta T is 100 degrees Celsius. So we have 10,500 more joules we need to apply. Okay, next. Now that my water is at 100, we need to boil that water. Let's do the mass times the heat of vaporization. 25 grams times 2,250 joules per gram. Again, you will be given this value. You do not need to memorize this. Get 56,000 joules about. And then lastly, it asks us to turn that ice to steam at 150. So we need to take that water at 100 and turn it into steam at 150. So we have MC delta T. We have 25 grams. Now again, the specific heat of steam is 2. And we're going from 100 to 150, so that's a delta T of 50. So we get... Okay, now we add together all of these values here, and we end up with 78,970 joules. And again, this is as long as you can get having to add together all 5. Okay, let's do a little conceptual question here again, bridging together the specific heat concept and the heating curve concept. So what would be the final temperature if a 10-gram ice cube was added to 250 milliliters of water at 2 degrees Celsius? Let's do a little picture here. Now what's going on here is energy is going to be transferred from the water to that ice cube. So it looks like this is a Q equals negative Q type problem. Now, what's gaining energy would be the ice cube is gaining energy. So we have how much energy is being gained. Well, we can measure that by how much energy it takes to melt something. So we're going to have 10 grams of ice melting. Remember, we need to use the heat of fusion here, 334 joules per gram. So this is the energy absorbed by the ice cube to melt it. Now what's going to happen in the water? The water is going to lose energy and cool down. So we are going to use MC delta T here, 250 grams of water, specific heat of water, and the delta T would be temperature final minus temperature initial is 22. Now again, this negative and this negative will cancel here to kind of get rid of that. So when we solve for TF now, it says that TF is going to be 3.2 degrees Celsius. Now this problem is a little challenging. I think you could maybe guess your way to the final answer, but let's think about what we have here. The ice cube cooled the water down to 3, but what's the temperature of the ice cube the second it melts? The second it melts at 0 degrees Celsius. So I think we need to think about thermal equilibrium now. We can't have some of that water at 0 and some of it at 3.2. They're going to kind of stabilize here. So I would say this, you have 0 grams of water, you have 10 grams of water at 0, and you have 250 grams of water at 3.2. And then your total mass is 250 plus 10 would be 260 grams. So you do this thermal equilibrium problem, and we find out that the water actually cools down a little bit more, down to about 3.1 degrees Celsius. Maybe you would have guessed 3.2 anyways. Okay, last challenging problem here. A 1 kilogram bar of iron at 300 is added to 1 liter of water at 95. Can the bar cause any of the water to boil? Let's just answer this and kind of guess what the water final temperature would be, and then think about what that means if we add our information about heating curves. So again, this looks like this is a negative Q equals positive Q type question. The iron bar is cooling down, the water is heating up. So on the iron side, we have a negative, and then we have 1,000 grams of iron. The iron specific heat was 0.45. And the iron is changing from temperature final, and it started at 300. Now on the water side, this is all positive. I guess I technically don't want that. So we have 1,000 grams of water. Water specific heat is 4.18. And the water is going to go temperature final minus it's starting at 95. So since we already learned last class how to solve for temperature final, I'm just going to go ahead and say that once you solve for temperature final, it ends up being 115 degrees Celsius. Now, let's just answer this question conceptually now that we did some kind of quantitative reinforcement here. Can water ever reach 115 degrees Celsius under normal conditions, liquid water? No, it boils at 100 here. So I would say if you add that metal bar to the water, now I'm not going to make you go so far as to actually calculate how much. We could do that. I would say since this final temperature is greater than 100, some of it must be boiling then. Now, probably not all, but some of it's going to be boiling due to that iron bar, because once it reaches 100, what's the energy going to do? It's going to start cooling off that, or start increasing the temperature of that water. Okay, I hope this helped, and ask questions in class.